So we have a uniform disk with an initial angular velocity of 3.3 revs per second, or 6.6 pi radians per second. We have a radius r. For the rod, the mass of the rod equals the mass of the disk. We know that the length of the rod is going to be 2 times the radius of the disk, and it is dropped on the disk. So the moment of inertia of the system would be equal to the moment of inertia of the disk plus the moment of inertia of the rod. And in this case, this is going to be mr squared over 2 plus ml squared over 2. And this is going to equal mr squared over 2 plus 4mr squared over 12. And the moment of inertia of the system is going to be equal to 5mr squared over 6. Now, the conservation of angular momentum states that Li equals L final. So that means that omega initial equals I final omega final. This is simply the formula for angular momentum. So the final angular velocity would equal the initial moment of inertia times the initial angular velocity divided by the final moment of inertia. And here we're going to have I initial will simply be mr squared over 2. I final will simply be 6 over 5 mr squared, and then omega initial will simply be 3.3. So this cancels out with this, and this turns into a 3, this turns into a 1, and this becomes 3 times 3, 9.9 divided by 5, essentially 1.98 revs per second, or we can say 12.441 radians per second. So this would be our final angular velocity after the rod is dropped onto the disk. And that's the end of the solution. Thank you for watching.